And we are happy to have Alex Steiger from Duke University, who will talk about decomposing the complement of the union of cubes in free space. Alex, please.
Thank you, Dan, for the introduction. Hope everyone can hear me. Right, so this is work on decomposing the complement of the union of cubes in 3 dimensions. It's joint work with my advisor, Pankaj Agarwal at Duke, and Mika, who might be attending the seminar. Good, so let's get into it. So in this problem, we have a set of n axis-aligned cubes in 3 space. We'll denote that set by C consistently, and we'll denote its union by U. We'll count the complexity of this union by the number of vertices on that union, which we'll denote by K. And this union complexity, as we'll see, is closely tied to the partition size of the complement. And it ranges from constant, say in the instance where a cube contains all of the other cubes, or up to n squared. And we can see this illustrated here with very large cubes, which kind of are slightly staggered and create a staircase. And then smaller cubes nibble out each of those long, thin stairs. And so this will end up with those thin linear number of stairs being nibbled into n each and quadratic overall.
Alex, Alex, I have a question. Are you going to talk about the composition of the complement? You are going to talk about this.
That's right, yes.
Okay, okay, go ahead, sorry.
Sure, yes. Yes, that's where we're headed.
Okay.
Right, so when the cubes are all the same size, the union complexity is known to be just linear the number of cubes. And the very problem we would like to consider in this talk, in this work, is decomposing the complement, or really partitioning into pairwise disjoint boxes, the common exterior of those cubes. And the natural question is how small of a partition can we compute, and how quickly can we compute it? So this union complexity K is a lower bound, roughly on the size of any convex decomposition of the complement. And we would like to meet that bound. So we want a linear bound in the number of n cubes and K the union complexity. And this problem, besides being a fundamental problem in computational geometry, has applications in collision-free motion planning, solid modeling, and others. So for now, of this talk, we're going to go over some background and related work. We'll then discuss our results, the performance of our algorithms. We consider 2 cases: the general case where the cubes can be any arbitrary size, as well as where the cubes are all the same size. We'll then give an overview of our algorithm for that general case, and we'll sketch its analysis at the end. So as a warm-up, we'll actually first consider the problem in the plane. And here we will consider rectangles as opposed to maybe squares, the analog of cubes in the plane. So we have a set B of these rectangles, denote again its union by U, and we want to partition the complement of the union of these rectangles into few regions. And the goal that we have set out can be achieved. The goal of getting linear dependence in both n and k can be had here. And that's using the well-known trapezoidal decomposition, or more generally, the vertical decomposition, as it's known across all dimensions D. And this is performed by taking every vertex of the union and erecting a segment up and down in each direction until another edge of the union is reached. And so you can see an example of this in the given figure. Unfortunately, when we consider that problem in 3D, where we don't have cubes but boxes and the side lengths can be arbitrary, Patterson and Yao give a construction where we're not able to partition it into as few boxes as we desire. So in particular, they provide this construction as seen in the figure on these very thin pairwise disjoint rods. And these rods are pairwise disjoint, so the union complexity is linear in n. However, you can see that any convex decomposition of this complement has size order n to the 3 halves. And the reason we end up with this lower bound is you can see that for any any point local to these 3 rods. So for example, I think you can see my cursor. Let's see. Say this point here, near not the intersection of these 3 rods as they are disjoint, but very close to it, that point, if it belongs in a cell in the partition of the complement, cannot reach any other similar point at any other near intersection of the rods. And they're n to the 3 halves of these points, and hence it gives a lower bound on the size of any decomposition. So this is motivating considering cubes in 3 space. The boxes don't have enough structure, and this goal of near linear dependence, or linear dependence as we truly want, can't be achieved. So now let's consider the problem of 3D cubes. What can actually be done for that problem? And if we consider the vertical decomposition aforementioned for the 2D case, can be generalized to any dimensions. We'll consider it here in 3. And unfortunately, the resulting partition has size at least quadratic when k is linear. And we can see this by taking these 2 opposing staircases. So on the bottom, we have this blue staircase, which I haven't shown the rest of the cubes, but we can construct this staircase behavior out of cubes. And erecting a prism upwards from every face of the bottom staircase is going to intersect each of the individual stairs above. And so each of the linear number of stairs in the bottom staircase will lead to itself a linear number of cells that meet the stairs above it. So using some more recent techniques, the slicing theorem of Aronov and Charrier ends up with a partition size n squared. We note that k doesn't show up in this factor here because k is bound itself by n squared. Using techniques from Patterson and Yao in the same paper from which that lower bound we just described for 3D boxes was described in, we can get k to the 3 halves. And so using either of these two still are a far cry away from the linear, if not near linear, dependence on n and k that we desire. And that's what we achieve in our paper, is this near linear dependence. So we come close. We give 3 algorithms. The first 2 algorithms are for cubes of arbitrary sizes. Their third algorithm considers a special case where all cubes have the same size. And we can see that we're only a small number of log factors off of our goal in all cases. And the second algorithm is a slight improvement over the first one when k is larger than n. Okay. So please stop me if there's any questions, as Dan mentioned. Because now we're going to transition to discussing our algorithm for the first one mentioned in this table. Okay. So the setup here is we're going to take a cube that contains the union of all input cubes, denote that cube by h, and we're going to recursively partition h into smaller boxes until each of those boxes, the interior of those boxes, is not intersected by the boundary. Of course, in that instance, then all of the boxes are either contained in the complement or in the union, and we'll take those that lie in the complement. So again, initially we'll start off with just this cube h. The space around h can be easily decomposed, so that we can focus on just h that bounds the union. And we'll denote a box in this partition that we're growing to be active if there's still work to be done. That is, the interior of that box is indeed intersected by the boundary. Every step of our algorithm at a very high level is to take some active box in our partition, and we'll split that box into 2 by some cut. And so an illustration of the cut can be seen here in gray. So what is this figure? We have an instance where the union is composed of simply 1 red cube and 1 blue cube. And the cut is referring to the rectangle specifically in the interior of the box. We've enlarged it for visibility, but this cut is becoming a face of the two resulting boxes. So the back face of this left box and the front face of this right box. That is the so-called cut. And as mentioned, whenever we have no active boxes, we're done and we simply report the boxes that lie in the complement. So what does splitting a box entail? This is the crux of how we, how do we choose the cuts to make? So splitting a box, as we can see in this example, may subdivide faces of the boundary. In particular, if we look at the top face of the red cube, it's being split into each of the two resulting subboxes. And in a sense, this is creating work for us. Informally, the more pieces that we are creating, cuts in the future will have to be made so that they appear on the boundary. So more generally, let's take a look at this figure down here of different cases for these fragments, these parts of the boundary that might intersect a cut in gray. Excuse me. Right. So loosely speaking here, a fragment, which is some part of the boundary that's lying in the interior of one of these boxes, might become trapped by the cut. And this is, we're making progress in this case. This V1 here is an example of that. After that cut is made, it lies on the boundary of the resulting boxes, and hence it will never be split into further fragments in the future. On the other hand, we see Phi2 is being split into just two pieces, but Phi3, this is a more complicated face of the boundary, it's actually being split into multiple faces by that cut. For a concrete example of a trapped fragment in the original example here, this blue face here that lies on that cut, and hence it does not appear in either of the two subboxes. So one thing is for certain is there are these so-called free cuts that will only trap fragments and do not divide any other further, do not divide any fragments further in the process. So what are these so-called free cuts? They are defined by faces of the boundary, which intersect a box, but the edges of that fragment lie on the outside of that box. Of course, no other faces of the boundary cross than this face of the boundary, and so no other fragments are being divided in the process. Readably will implicitly be making these free cuts as soon as possible whenever they show up during our algorithm. Right. So the main idea for the analysis, or to work towards bounding the size of a resulting partition, is that we have this relationship between the size and the total number of fragments in which any of the faces are split. This comes with a caveat. We have to be a little particular about what kind of cuts we're allowed to make. So we'll mention that here, and then we'll kind of ignore this point as a technicality throughout the rest of the description of the algorithm. And so what is a useless cut? We might be, as the algorithm as we describe it in the following, we might be making a cut such as R1 or R4, which splits the box into two pieces where nothing lies on one side, and it does not even trap a fragment in the process. So we can see the cut R4 is trapping a fragment, where so the blue is the union, the boundary of the union in this 2D example, and R2 is separating the boundary into two subcells, but R1 and R4 do not do this. So we'll make this point now, and then we'll implicitly be avoiding making these useless cuts. Right. So by kind of extending a argument by Chabot from binary space partitions, we have the following. If our partition is done in such a way that any axis-aligned segment that lies on the face of the boundary is only being divided by, say, lambda cuts, these rectangles that we're splitting our boxes by, the total number of fragments that we create is order k lambda squared, where again, k is the union complexity. From the aforementioned fact above, this bounds the size of a resulting partition. And our main contribution is describing our partition in a way so that lambda is bounded by log square n. The resulting size of our partition is hence k log to the 4n. So before we move on to the details of the algorithm, I think I'd like to give some intuition behind this extension from Toth. So the first step is to generalize from segments to how many times is a rectangle being divided. So if the segment is being divided lambda times, we'll say that we'll show that a rectangle on the boundary is only being divided into lambda squared fragments. So let's look at kind of how this face of the boundary is being cut over time. And maybe there's a first cut that splits into 2, 3, and so on. And eventually the algorithm is going to trap one of the fragments by one of the cuts that it's being made. And that's what we'll show in this dark gray. Continue to make cuts. And eventually we'll get to, we might get to a scenario where we have a portion of the face that lies strictly in the interior of a box, and that is a free cut. The box, the intersection of the box is strictly in the interior of that face or of that rectangle. That is a free cut. So our algorithm will immediately make that cut, and henceforth that part of the rectangle will no longer be divided. This is the main way we're able to bound the number of fragments being made. Okay, so this might happen again. Another free cut gets made. And at the very end, we have the subdivision of the rectangle we started with. By the property that every line segment on a face is being divided only lambda times, then a line segment on this rectangle, which lies on a face, is only divided lambda times. And so the total number of vertices in the subdivision of the rectangle is only order n on each edge of the rectangle. In fact, it's at most lambda. And so let's consider one of these segments defined by these 2 vertices of the subdivision. And at a high level, we're going to charge vertices of this subdivision to the segments on the outside. So if we look at the evolution of the subdivision leading to that segment S, which will highlight these edges in black as the algorithm, as these cuts are being made, we can show that we can charge the vertices that define these segments leading up to S is only order lambda, because if we take the ray perpendicular to S to the opposite side, it's only going to cross, again, by assumption, only lambda cuts. So we'll be able to charge the edges of these segments, that is the vertices of the subdivision, to these edges on the outside, where each of the order lambda segments is charged order lambda times. And in total, the total complexity of the subdivision is lambda square. The number of vertices is proportional to the total number of fragments being made, and hence we have the claim set out. So with this in hand, what we can do is take a face of the boundary with, say, kf vertices, and we partition into rectangles, order kf rectangles using just the vertical decomposition. We can then apply the aforementioned bound for rectangles to each of those rectangles locally. And so that face is going to be divided into kf lambda square fragments. And taking finally the sum over all faces of the boundary, we end up with k lambda square as stated. So just to recap, that was the extension from Toth, and that leads us to desiring coming up with this partition B so that this lambda is bound by log square n. And so now we'll get into our actual algorithm. Our partitioning of the complement is itself going to be guided by another decomposition scheme. namely an octree, which I'm sure this audience is familiar with. So this is a hierarchical decomposition of the space represented by an 8-ary tree. We'll define it with respect to some point set P. We start off with a cube containing the entire point set, and each node is a cube, which is then subdivided into congruent 8 cubes at the child nodes. At the leaves of this tree contains at most one point in each of these cubes, and we know that if the spread, that is the distance between the farthest pair of points over the distance between the closest pair of points, if the so-called spread is polynomially bounded in the size of the point set n, then the height of the tree is only log n. And the height of the tree being log n is a key component to our argument. Okay, so we'll talk about how this octree is being used to guide our partition in a moment, but we still have a couple concepts to introduce. We have this notion of long and short cubes. So we'll call a cube C long if none of its vertices lie in the interior of some box B that it intersects. And so we can see an example of this on the right, where we have this blue box C, which is intersecting the smaller, this blue cube C intersecting a box B, and none of its vertices lie in the interior of B. And the key property we'll need is that when B is a cube, as shown in this figure, C contains some edge of B. So in particular, if B is an octree cell and C is one of our input cubes, one of our that input cube C will contain an edge of B. And we'll flesh this idea out, just foreshadowing for our algorithm in a moment. So that's long and short. And so finally, what we'll do is kind of restate the goal of our algorithm, which will be useful for our purposes. We'll introduce this notion of voidness. So of course, every face of the boundary lies on the face of some input cube. So we're going to say that a box in our partition, as it's evolving, is void of one of the input cubes if none of the boundary faces on that cube intersect the interior of the box B. So of course, if a box is active, then some part of the boundary intersects its interior, and hence B is not void of whichever cube contains that face of the boundary. So we'll restate our goal as computing this partition for which every box is void of every input cube. Just kind of restating what we already know. Once a collection of boxes are void of a cube C, as those boxes are further split by the algorithm, it's not cutting through any of the faces on C. So there's a concrete example here. We can see that after the cut is being made, that left box is void of the blue cube. And in a sense, progress is being made. Okay. We'll go slowly through our algorithm, but it, in fact, will actually fit all on this slide, more or less. So we're going to start off, again, with some box that contains the union, that's H, and we're going to build an octree with that being the root region, which is, again, a cube, and it's going to be over what point set the vertices of the input cube C. This octree will guide our decomposition recursively because we're going to do a reversal, a pre-ordered reversal of the tree. So what happens at a node U during this traversal? Let's call the cube at a node RU, and let's denote by this set of boxes in the partition intersecting the cube RU as XU. And so here it's significant to mention our algorithm is going to be making many cuts across the boxes. And when we say XU, we're always going to be referring to the current value of XU at that moment. That is, at that moment, what is the set of boxes that intersect RU? It'll be dynamically updating at while we're processing node U. Okay, so the first step is to make the boxes in XU void of specifically which input cubes, those that are long for RU. So this is where everything starts to culminate. By induction, it's going to be sufficient to only make XU void of what is long at RU and short at the parent, because everything that is long at the parent is also long at the child, and it will already be void of those cubes. So what we need to do via some processes make XU void of what is long in RU and short at the parent. After we make those the cube long of what is, sorry, void of what is long, we then have to do some simple cuts just to make XU fit, the boxes in XU fit in the child cubes. So this is a straightforward process, being that there are 8 children. And lastly, if we have a leaf node, by induction, and after doing step 0 at that leaf, it's going to be void of all cubes save for one short cube, because at a leaf node of the octree, there's only one vertex in the interior of that cube. So any cube that intersects RU at that point must is either long or short, and everything is already void of everything long above. Okay, so that's the setup. Of course, the crux is how do we perform step 0. Step 1 and step 2 are less interesting, and they consist of doing some constant number of cuts locally to XU. But afterwards, the boxes in XU will be void of all input cubes. Are there any questions for this setup? Because the remainder of this algorithm will be discussing how do we do step 0. Great. Okay. Right, so step 0. Let's denote by CU the set of cubes that are, again, long at U and short at PU. This should really say long at RU and short of RPU, where PU is the parent of U. And since RU is a cube, all of the cubes are going to contain some edge of RU as RU is a cube. So let's fix an edge E of RU, and let's look at the cubes in CU that contain it. Our goal again is to make XU void of specifically this subset of cubes, CE, using so-called staircase cuts, which we'll introduce in a moment. And then we're going to repeat this for every edge of the box, because every cube in CU contains some edge. This will achieve the original goal of step 0 to make void of all cubes in CU. Okay, so just rotating that figure a little bit, this really becomes a 2D problem. So we have the union of these cubes, and the boundary of those cubes within RU makes this monotone rectilinear chain. We call this a staircase. What we're going to first do is make a pair of cuts along the median stair of the staircase. And so if we take XU and every active box within it, we are going to split it by these median cuts. So for example, we have box B here, and this median cut is cutting through. We will separate, we will perform that cut and split it into 2 pieces. And we'll do this for every active box. After doing this, we then can recurse in the top right and the bottom left, as we have more of the same. The top left box is fully contained in the complement, and the bottom right box is fully contained in the union, and hence all the boxes in XU at that point are done. And we recurse, and so we'll perform this computation. And the key insight, or the motivating factor, going back to trying to bound the number of times these segments are being cut, this simple procedure of staircase cuts is only cutting these axis aligned segments in R, be it on the boundary or just generally in R, only log the number of cubes that we have. So log of CE, which is of course bounded by the total number of input cubes, log n. And so that's why we do the staircase cuts in this fashion as opposed to anything more naive. Right, so that concludes the how we do the staircase cuts. And now let's summarize kind of the impact of doing them in this way more globally. So an overview of the analysis. Generally, at one round of these staircase cuts is cutting any segment log n times. And hence it's not hard to show that then locally at a node U, all of the cuts being performed. So a round of staircase cuts for each of the edges of RU, and then either the constant number of cuts to split the boxes they fit in the child cubes, or if it's a leaf node, the cuts to make void of the final last short cube. This is a constant number of cuts. So in total, we have a constant number of log n rounds plus some additional constant cuts. And that is to say, a segment RU is cut only log n times. And the punchline is that from here, we can show that any line segment on the boundary is being divided log square n times. So let's slow down for a moment. The way that we do this is considering some segment S, and of course, S lies on some face of an input cube. If we suppose that that cube is long for the parent of a node we reach, so let's consider node U and look at its parent PU. If it is the case that C is long there, then when the algorithm comes to visit node U, it's already going to be void of that cube C. As a result, C will not be divided at U because it lies on C. Hence, the segment S is only going to be divided if C is short at the parent. And let's count how many nodes there are. C is going to be short at only 8 nodes, at most 8 nodes per level. There are 8 vertices of C. And hence, by the key property that the octree has height log n, there are a total of log n nodes for which the segment S is being cut, and it's log n times each. So in total, the segment is being divided only log square n times. So is there any questions about that argument? Good. So this is very much what we were trying to show, right? We were building up from what is the size of our partition down to just trying to bound the total number of times any of these line segments on the boundary are being divided. So this ended up leading us to our first result, which is a decomposition of the complement of size k log to the 4n. With the remaining time, I'd like to give a high-level overview of how we slightly improve it by the second algorithm. That's right.
Alex, do you have a simple
Yes, sir.
example where you can show the decomposition, how it looks on a very simple example?
Unfortunately, I do not have an example of that in 3D.
Okay.
Right, so let's maybe just get the high-level idea for reducing that partition size, reducing the log factors on K. So we had this notion of free cuts, which was used heavily in that lemma earlier. And the idea is to use this weaker condition. So what is the definition of free cuts as stated currently? Or it's where a face of that boundary is separating that box into 2 pieces. But this is more than we need, because we can instead just look for when a face of an input cube has that property. It's splitting the box into 2 pieces. We don't have to wait until exactly part of the boundary on that face crosses it itself. And so tested intuition. Of course, it's free in the sense that there are no boundary faces crossing through a face of this input cube as they lie in the union. So we have at a high level, we have the same property, but how does this manifest in the analysis? So graphically in this figure on the right, we have an example of a square face S, and in 2D, a box B that's intersecting through face S. And phi1, phi2, phi3 are fragments of that lie on S. So what is shown in blue is the interior of the union, and what is white and gray is the part of the boundary that lies on S. And this new definition of free cuts, we're able to make a single cut at this very moment during the algorithm and split that box B into two, which will trap each of those fragments. Phi1, phi2, and phi3 all become trapped in one moment, as opposed to with the previous definition of free cuts having to wait until phi1, phi2, phi3 individually are free cuts. They themselves separate B. So what was the old lemma? This is kind of retelling of it. If every axis aligned segment that lies on that face of the boundary is divided by lambda cuts, then we showed that we'll create KF, where KF is the number of vertices of F, times lambda square fragments. With the new lemma, we're able to show that with these new free cuts, we're able to improve this and show that any input face on the of an input cube, the total number of fragments that is divided into is only lambda square plus a linear order of lambda on KS, as opposed to quadratic in the previous old lemma. So doing the sum again, let's sum over all the total number of vertices that we, the total number of fragments that we create. Well, there's n input faces S, and so we get n lambda square plus only k lambda. Our choice of lambda by our algorithm, because everything else stays exactly the same, save for this new definition of free cuts. And so it's log square n. And that's the resulting size of the new improved algorithm. And just to summarize our results, we have these three algorithms. We heavily focus on the first one for partition of size k log to the 4n. We just gave a high level idea for the second algorithm. And for what I imagine would be a lack of time, we were not going to discuss the details of the third algorithm, but it's quite different from the algorithm we described here. We need a lot less machinery. And by exploiting the fact that all the cubes are the same size, we're only a log factor away from a linear in n. So we have some two open questions to leave you with. One, can we actually achieve the goal? And if not, what is the lower bound? What is the construction that leads to it? And second, can we extend any of the ideas here up to higher dimensions? This notion of octrees and staircase cuts and so on seem to generalize in some fashion to higher dimensions. So decomposing a space in 4D and so on, which would be useful in robotics for, say, a configuration space, would prove useful. This actually concludes.
Thank you very much, Alex. Let's thank Alex in the limited means that we have. Other questions? Any questions? If there are no questions, let me ask one more question. I'm not sure I got all the details, but when you look at one cut of your decomposition, it looks differently. It may look differently on the different sides, right? On one face of the decomposition.
Sorry, can you repeat the question?
Is your decomposition a cell complex or not? Does it mean if you have one face is everything that coming from here crosses through this face. Is crossing through this face.
So it very well may be the case that a face of the boundary might be supported by faces of many boxes. If that answers your question. I'm not sure about what it means to cross through the boundary of a box.
Yeah.
Then this is Pankaj, it's not a cell complex.
It's not a cell complex, but then I want to ask a question. How complex is the overlay on each of these faces? And the reason I'm asking this, can you give an answer to this? Because this can be crucial in certain uses of the decomposition of the complement. Is my question clear?
What do you mean by overlay?
I mean, you have a facet of the decomposition. Some walls come from one side and some walls from the other side. I look at the overlay of these two patterns on the facet. And I argue that this number is crucial in certain applications. And I wonder if you guys know to bound this number.
No, that's a great question, Danny. I don't know. That's a very good question. We haven't thought about it.
Okay, I'm just asking it because we get stuck again and again in various applications because we don't have a good bound on this overlay. So I'm just sharing this.
Okay, without thinking much, I believe that it might be possible to refine this decomposition so that the overlay complexity has only polylog overhead. It's not quadratic.
Okay.
I think. But one has to refine the decomposition further.